All right, welcome everybody. We have an exam next week, so hopefully you've been aware of that. I'll go ahead and tell you if you're one to look at the notes and print off notes ahead of time. Last semester, because we all got the stomach bug in my family and we all got sick all at the same time, the notes for Tuesday are not on Canvas yet. I'll have to make them over the weekend because I just didn't get to cover AC circuits last time, so we're going to add that in there a little bit, the RLC circuits and all of that fun stuff. But we have an exam next Thursday, so be aware, be prepared for that. By popular request, we'll have a little practice exam next Tuesday at the tail end of class. So what we'll do is we'll come into class, QR code for attendance, all that stuff will be on the board. We'll go through class as normal, and I will reserve the last 20 minutes or so for a practice exam. The exams will be on the front as you walk in, so you can grab them and just have them ready to go. But we won't actually pull those out and use them until the very end of class. So be aware of that if you want to come prepared for class. I'll be trying to get things out and prepped ahead of time, but also be writing your exam for next Thursday as well. So there are many moving pieces between now and next Thursday. But yeah, the exam next Thursday will be on, let's see, current, no, we already did that. Let's see, what's the exam next Thursday on? Let me find that in my notes. This is Phys 2. Phys 2 schedule, let's see here. So it will be on chapters 25 through 28. So yeah, current and resistance, Kirchhoff's rules, magnetic forces on charged particles, magnetic fields of charges and currents, and then a little bit on RL circuits and things along that line. So inductance, magnetic energy, RL circuits. So I guess we won't be covering chapter 29 until after the exam. So I misspoke. But we'll have to try to get into that. Likely because I didn't get it done ahead of time, I will post an additional helper homework because I didn't add RL circuits to your chapter 28 homework, and I feel like it's a bit late to do so now because we want to have it for Tuesday. I'll post an additional homework for 0 points, but just will give you a chance to practice on RL circuits and the stuff that we're going to cover Tuesday. So what we're covering in class on Tuesday of next week will be on the exam, but it will not be on your homework that's due Tuesday. It'll just be posted as an additional no points homework just to give you practice with this kind of stuff. So just be aware of that going into it. Are there any questions before we move back into what we were covering on Tuesday of this week? All right, so last time what we talked about was magnetic flux. We talked about magnetic flux is how much magnetic field passes through a given region. You can do an integral over that region if you have a non-uniform magnetic field or you have a surface that is formed by a contour that has curve to it. In this problem, a uniform magnetic field, so we checked off that box, is in the x direction and it makes a constant angle, the surface of the wire loop makes a constant angle with respect to the magnetic field, at least part A, part B, part C, and part D do. And so for each one of these, when the magnetic field is constant and the curvature of the surface formed by the current loop is constant, what we end up getting was that magnetic flux was equal to NBA times the cosine of the angle between the magnetic field. So theta, if you can imagine, this is our wire loop right here. And you can think that N is going into the board a little bit here. Actually, let's use red since the magnetic field is in blue. So N is going to be in the direction going into the board. It's normal to the plane of the loop. and the magnetic field is going to the right, as suggested by the figure. In the x direction, the angle theta that is shown here, the angle theta is the angle between the magnetic field and the direction that is parallel or perpendicular to the plane of the loop. So in part A, when theta is 0 degrees, that also means that the normal vector is going to be aligned to B. So you would get phi is equal to NBA times the cosine of 0 degrees, which in this case, the cosine, well, in all cases, the cosine of 0 degrees is 1. So we've just got NBA. It says that it's a magnetic field strength of 0.2 Tesla. It says that we have 5 centimeter long, so this would be L here. L, the length of the side. So the area is going to be L squared. And a single turn, so N is equal to 1. So this is a fairly straightforward problem in the sense that we've got now B times L squared, so that's going to be 0.2 Tesla times a centimeter, 5 centimeter side, so that's 0.05 meters squared. And this comes out to be a value of, if I can go back to my notes, a value of 5 times 10 to the minus 4. And we said that the units of Tesla meter squared were the units of Weber. Not exactly an exciting problem, right? I mean, we just ended up multiplying two things together. But remember, what is the important, why are we even wrapping our minds around what magnetic flux is? Like, what are we building towards, if you remember the tail end of last lecture? What's magnetic flux? What's the importance of magnetic flux? Yeah. The important thing is not necessarily what magnetic flux is at any given time, but how it changes. Because when magnetic flux changes, you'll get an induced current, an induced EMF in this loop. So you can imagine, as we go from A to B, in part B, the flux is going to be equal to N, which is 1, times BA cosine of 30 degrees, which you would end up getting would be 4.33 times 10 to the minus 4 Weber. So we have had a decrease in magnetic flux to the right, and so what ends up happening is we would try to recover that loss of flux by inducing a magnetic field that would favor the direction of B, and the way that we do that is there would have to be an induced current, an induced EMF, inside the wire loop as we go from A to B. And then as we go from B to C, where the flux is equal to BA times the cosine of 60 degrees, in which you would have 2.5 times 10 to the minus 4 Weber, then you would get more, a continued induced EMF and an induced current going around this loop, because we have again had a change going from B to C in terms of our magnetic flux. And part D, what do you expect the magnetic flux to be? 0, right? Because now the normal vector, which would be going in this direction, in the minus Z direction, so actually maybe I should draw it this way, opposite to Z. Minus Z hat is going to be equal to the normal vector here. If I take the dot product between those two, I would end up getting the cosine of 90 degrees, the cosine of 90 degrees, which is 0. So during this process, because I get a drop in flux, I would end up having to have an induced EMF to make up for the change in flux here. I would end up getting a current inside of the loop. But we'll get to how we calculate that here in a second. And remember, I can't remember who asked the question on Tuesday, but how can we induce a current inside of our current loop? In general, it is very difficult to change the number of loops present at any given time. That's kind of a fixed quantity. You're an electrical engineer, you design a transformer or an inductor with a certain number of turns, so N doesn't really change. However, you can change the external magnetic field strength, you can change the area of your loop, or you can change the orientation of the loop. Any one of these are going to cause a change in magnetic flux, which in turn is going to induce an EMF inside of your current loop. If none of those three things are changing, the magnetic field strength, the area of your loop, or the orientation of your loop, in that case, you get no induced EMF. If magnetic field strength, area, and orientation are not changing. Okay, let's step up our game a little bit here and do one that is maybe not quite as straightforward. A circular coil has 15 turns, so that's our magic number N that was given to us in the equation. It has a radius of 4 centimeters, and don't forget then that A is equal to pi r squared, and is in a uniform magnetic field of 4 kilogauss. So this is our magnetic field strength B. Find the flux through the coil when the unit normal to the plane is in the I hat direction. So it says that our magnetic field is also in the X direction, so I hat. So the normal is in I hat plus J hat divided by root 2, D K hat, and E partially in I and partially in J. And what we have kind of glossed over here, when we write down that our magnetic flux is equal to NBA cosine of theta, where again, if this is N hat, and this is B, then this would be theta. If you look back in your notes to the integral form, we didn't state this in terms of BA cosine theta. What we said was that it was a dot product. And so when the field is constant and when the orientation angle between the field and the normal is constant, then we could also state this as B dotted into A, where A as a vector is going to be the area times N hat. So you imagine our current loop is going to look something like this right here, where the normal is going to be out of the page or above the page like so. If it has an area A, then all you have to do is multiply the area A times the direction, which is given to us in A, B, C, D, and E. So for part A, if you want to know the magnetic flux in this case, you end up getting N times B, which is going to be B in the I hat direction, dotted into the area A, which in this case is also in the I direction. So we have that these two directions, the normal vector and the magnetic field, are parallel to one another. And when the unit vectors are parallel, then what you end up getting is a dot product that is maximized. So this is just NBA. So 15 times 4 kilogauss. Let's see, 4 kilogauss. I think if we think about this, there's, I think it's 10 to the minus 4 Gauss. No, 10 to the minus 4 Tesla. Somebody look up this conversion for me because I didn't write it down in my notes. in 1 Gauss. Make sure that's the correct conversion. That's correct? Okay. So that means that 4 kilogauss is equal to 0.4 Tesla. So we've got 0.4 Tesla times an area, which would be pi times the radius of 0.04 meters squared, which comes out to be 30.2 milliweber. Bill? I don't mind pulling up the QR code real quick. No problem. So without doing any work whatsoever, looking at part B, what do you expect the flux to be? 0. Why? Right, so the unit vector for the magnetic field is in the x direction. The unit vector for the flux is in the y direction. For the area is in the y direction. Those two are perpendicular to each other. And the dot product between perpendicular vectors is just 0. Right, so part B, there is 0 flux. You could also think of it as the normal vector is in the y direction, so going towards the vertical in our classroom, but the magnetic field is in the x direction. You imagine if an arrow were traveling from left to right or right to left across the classroom, and it did not fall, then what would happen is there would be 0 chance of that arrow going through my tablet, right? Especially if my tablet were infinitesimally thin, which we're assuming here. So in that case, there's no flux. Part B then states that there's no parallel components here, so you get 0 flux through that region. Yes, so if you look at part D here, part D also K is perpendicular to Z is perpendicular to X. So you would also get that the flux is 0 for part D. For part C, you get N, the flux phi sub m is equal to N times B in the I hat direction times A, which is multiplied times I hat plus j hat over root 2. Well, the component that is dotted into the j direction is going to go away to 0. And so you end up getting n times b times a, where the I components survive. So this is equal to nba over root 2. So take your answer to part A, divide by square root 2, you would end up getting 21.3 milliweber. Yes? Right, you don't worry about any perpendicular components. Yes, because magnetic torque is a cross product, right? Cross products depend on things being perpendicular. They are strongest when things are perpendicular. Dot products are strongest when things are parallel. So it's because torque is a cross product, perpendicular matters. Here, this is a dot product, parallel things matter. Good question. Part D, you get phi sub m is equal to n times b in the I direction times a which is in 0.6 times I hat plus 0.8 times j hat. You can verify with some quick math. If you take 0.6 squared times 0.8 squared and take the square root of that, of them added together, it comes out to be 1, so it is a unit vector. So we get 0.6 times NBA is all that survives, or that's equal to 18.1 milliweber. Questions on this one? My personal opinion about week-long breaks in the middle of the semester is wonderful. I always need Thanksgiving break and spring break. The week after both is such a drag. I can see it on all of your faces. So I'm glad you got the break. I'm sorry that you're suffering because of it. Do what? 2 tests on the week that you come back. Happy spring break. And if you're like me, when I was a student, and like me as a professor, you have great intentions for staying up to date and catching back up on things that you fell behind on. And then it's Saturday before school starts back on Monday, and you didn't do any of that. Yes, it should be. Thank you. Okay, let's get to where the rubber really meets the road here and look at number 30. The flux through a loop is given by phi sub m. I use the uppercase phi. If you haven't noticed that, I think I mentioned that when we did electric flux. Your book uses a lowercase phi, but it's the same thing. I just learned it with uppercase phi, so it's hard. Old habits die hard. But the flux you're given is 0.1 t squared minus 0.4 t, where phi is in Weber and t is in seconds. Find the induced EMF as a function of time, and find both phi sub m and the EMF at t equals 0, t equals 2 seconds, t equals 4 seconds, t equals 6 seconds. So part A, we're asked to find the induced EMF, and how would we do so? Well, remember that induced EMF is equal to negative change in d phi dt. So that's minus d, the derivative of 0.1 t squared minus 0.4 t, which is minus, multiply by the exponent, so 0.2, drop the exponent, so t minus 0.4, or that's equal to 0.4 minus 0.2 t. And that would be in volts. So the EMF, the induced EMF, changes as a function of time here, right? At one time it might be 1 volt, at another time it might be 0 volts, at another time it might be negative 1 volts. And that's something that most electrical engineers aren't used to thinking about, the idea of negative volts. Usually you think about it as just an absolute potential. But let's say in part B, we find that the induced EMF at one point is a positive EMF, and at another time, it's a negative EMF. What is the physical intuition of having a positive EMF at some times and a negative EMF at other times. What's that? Sorry, one more time. I can't hear you. Okay, so positive charge on one end, negative charge on the other. Typically, we're going to be thinking of loops, right? So instead of positive and negative charge being in different ends of a solid thing, if it's a loop, what does it mean if it's positive or negative? Yeah, so you end up switching the direction of the current, right? Effectively what happens is you have a change in EMF that goes from positive to negative. You flip the direction of the current. So now we're starting to get into at least the makings of, this wouldn't make for a good AC circuit, but you can see how if we can change the direction of the EMF based off of flipping the direction of the flux change, then we can end up building AC circuits. Here, you're going to end up getting something that is just a linear change in EMF as a function of time. So part B, we're asked for 4 different times. Let's just build this out as a table where we've got flux in Weber, and we've got the EMF in volts here. And so you've got 2, 4, 0, 2, 4, and 6 seconds. And so at time t equals 0, how much flux is passing through my loop? 0. Yes, that's absolutely right. If I plug in t equals 0 to this equation up here, I end up getting that there is 0 flux through my loop. But if I plug in 0 to my equation for EMF right here, then I end up getting that there is 0.0 volts induced in my current loop. So how do I have 0 flux, but I have non-zero EMF inside of my current loop? What gives? How do I have 0 flux but non-zero EMF?
The flux is 0, but it's decreasing.
Yes. Remember, it doesn't matter what the flux is at any given time. It matters how the flux changes. At this moment, the flux is changing rather quickly. You could plot this out here if you wanted to. If you took a plot, let me just not mess this up and trying to hand draw it. Go to your favorite plotting tool, go to Desmos, and let's figure out here and just look at our graphing calculator. We have 0.1 t squared minus 0.4 t. And we don't want that. I guess I have to use x. I think it uses x and y. So we've got this right here. And what we want is that the slope of this line is non-zero. So the flux is the red line, but the slope would be the induced EMF. And we want the negative of that. The slope would be negative. We take the negative of a negative, and we get a positive EMF here. At 2 seconds, you can expect that the flux is going to be negative. There is negative flux, so you could imagine it going into the board at that time. But what's the induced EMF? It's 0. The slope of my flux is 0, so the induced EMF is 0. Then I get to 4 seconds, I get 0 flux again, but I get a non-zero EMF, and then I get to 6 seconds, and I get a non-zero for each one of those. But you can kind of get a feel for it. We said that the induced EMF is going to end up being, let's see, 0.4 minus 0.2x. So you can see the purple line here. Actually, I kind of prefer reverse contrast anyway. It's easier to see. The blue teal line here is going to be our flux. The green line here is going to be the induced EMF. Okay? So let's look at that. You could use Desmos to calculate that if you wanted to, but you could end up calculating that you get minus 0.4 Weber at 2 seconds, 0 Weber at 4 seconds, 1.2 Weber at 2 seconds. You get 0, minus 0.4, and minus 0.8 here as we go on through the remaining time. If it told us that the flux changed as, say, instead of t squared, if it changed as a function of sine or cosine, this is the root for developing an AC circuit. Because if the flux changes as sine or cosine, the flux is constantly going positive and negative. And it is always having negative and positive changes. Right? The derivative of sine is cosine. So in that case, you always get a changing EMF, one that is an alternating EMF. The EMF would change as a function of negative cosine. So it would always be going negative, positive, negative, positive. It would always be reversing direction. Now here's a question for electrical engineers. Normally we think of DC circuits. You're sending power, electrons, along one direction, and you're delivering power by that mechanism. But if current is alternating, how are you delivering power to something? How are you delivering power to the load if all you're doing is reversing the direction of the flow of electrons over a function of time? I'm not asking you to answer that now. It's just worth giving it some thought. Because if you're electrical engineers and this is a physics class, I mean, the whole point of your education is trying to get a sense for how things work, right? I drive my car to work every day. I have no idea functionally how each of the individual units of my car work. I'm okay with that. There are certain things that I do, though, that I want to know to the nth degree how a star keeps from blowing itself apart or dying every single second of the day for, on the order of 10 billion years or whatever. As electrical engineers, it's worth at least wrapping your head around that, so that way it's not just magic to you. Just think about it. Watch a cool YouTube video about it. Last question, and then we'll jump into additional slides. A 100-turn coil has a diameter of 2 centimeters and a resistance of 50 ohms. Okay, so now you see that it gives us resistance. Our Faraday's law and Lenz's law allow us to calculate induced EMF. Generally, if there is a resistance involved, you're going to be asked something about a current. Or if you're asked something about a current, you've got to assume that you're going to have to calculate resistance somewhere along the way. So two ends of the coil are connected together. The plane of the coil is perpendicular to a uniform magnetic field. The direction of the field is reversed. Find the total charge that passes through a cross-section of wire. So now we're going a step further. We're going to have to calculate current based on resistance and induced EMF. But then if we're looking at total charge that passes through here, well, remember that current is related to change in charge. Whoops. Find the total charge that passes through the cross-section of wire. If the reversal charge takes 0.1 second, find the average current and average EMF here at any given time. Okay. So, let's draw this out. Initially, that's going to be too big. Initially, what we have is this right here, where the magnetic field strength, or the magnetic field itself, B, looks like so. And it's got a magnitude of 1 Tesla. And then sometime later, in part A, we don't know how much time, but in sometime later, what we've got is the magnetic field is down, still at 1 Tesla. So we want to find in part A how much charge passes through this region. How in the world would we calculate how much charge has passed through the region? Again, the first thing that we want to consider is induced EMF is equal to d phi dt. Or if we know what this could be in terms of a finite sense, delta phi over delta t. Pardon? Oh, yes, negative sign. Thank you. It turns out in this problem, we're only really talking about magnitudes anyway, so we're going to end up dropping the negative sign at some point. But yes, for completeness sake, we need the negative sign. Well, what's changing in this problem? The only thing that changes is the direction of the magnetic field, right? So the only thing that changes is, let's see here. You could consider that if n hat is in this direction in both cases, that theta is the only thing that changes. So we end up getting here that the induced EMF is minus NBA times, this is going to be weird notation, the cosine of, the change in cosine theta. I don't want to put it inside of there. Basically what I'm trying to say is minus NBA times cosine of 180 degrees minus cosine of 0 degrees. Okay, so that gives us the induced EMF over this period. But how do we calculate the amount of charge that passes through the cross-section of wire? Well, don't forget that in this case, induced EMF, or let me say EMF is equal to IR, which we're given, and I is equal dq dt. So do you see where we're going with this to link everything together? It turns out, at least the way that I solved it, I feel like it gives a little bit better significance. We're actually going to solve this problem in reverse, okay? It makes more sense solving it in reverse. So first we're going to look at the average EMF that is induced, because now we've got average EMF is exactly what we calculated right here. So that's going to be equal to minus N times B times A times cosine of 180 degrees, that's minus 1, minus cosine of 0, that's 1. So you end up getting negative 2. So we've got 2 times number of turns, that's 100, times, I'm forgetting here, in each one of these cases, we need a divided by delta t. So divided by delta t here. B is 1 Tesla. A is diameter. So R is equal to 0.1 meter. So we've got pi times 0.1 squared. That's NBA divided by the time that it takes, 0.1 second. This comes out to be an induced EMF of 628 millivolts. So not a lot of voltage here. But do you at least see how we calculated the induced EMF? Okay, part B, if you want to find the average current I is going to be equal to the induced EMF divided by R. So that's equal to, 628 millivolts divided by a resistance of 50 ohms, which comes out to be 12.6 milliamp. River? 0.0, yes, you're absolutely right, it should be. 0.01 meter here and 0.01 meter here. Assuming I didn't make any mistakes, I think that's still the correct value because you get a factor of, basically you get 2 pi here, so that's 6.28 times 100 divided by 100 divided by 10. So yeah, I think 628 millivolts is still correct. You can double check me on that. Is it not? It's what? It'd be 2 pi? Yes, so you end up getting, this cancels that, but then I've got 2 times pi times 1/100th divided by 1/10, right? So that's still divided by 10 overall, right? Okay. Up here at the top. I shoot myself in the foot a lot of times because I'll find the correct algebraic solution and then I use AstroPi to take care of the units for me. So that's why I don't have intermediate steps written on here and end up missing things. It saves me time when I'm writing solutions, and then it frustrates me when I'm in the middle of teaching. Now part A. Part A, we get that delta Q is equal to I delta T. So that's 12.6 milliamp times 0.1 second, or that's equal to 1.26 millicoulomb. I realize when we go through slides and when we do problems, it's easy to lose the forest for the trees. But let's take inventory of how far we've come in this semester, right? The problem is that I'm trying to get you to see is, first we discussed that there's this idea of charge, and then we introduced electric fields and voltage and all that kind of stuff. And we found that there are also things called magnetic fields out there, right? And magnetic fields exert forces on charges, right? The magnetic fields can cause charges to deflect. But then we also found that moving charged particles, currents, produce magnetic fields. So we have a bit of a chicken and the egg situation here. And we also said that a buildup of charge somewhere induces a voltage. But now we've got that changing magnetic fields also induces a voltage. And so I guess all that I'm trying to say is that I know Phys 2 is a tough subject, and you can see the reason that it's tough is because we keep adding on onion layers here of this is changing, so that means I have to account for this, and then that means that I have to account for this, and it's really easy and frustrating sometimes, but it's also very interesting because we have very deep interconnected workings between electricity and magnetism here. In fact, that is what the whole idea of an electromagnetic theory class is about unifying these things that appear on the surface as two very different things, but are actually two sides of the same coin. I don't know. Maybe you find that interesting, maybe you don't, but as difficult as this class is, it's why I love this class, teaching Phys 2, at least. Okay, let's switch gears and discuss something new about other ways that we can calculate EMF. Why didn't that go full screen? You can sign in. I looked ahead of time. I don't think that there are any multiple choice questions or anything, but if you have questions at the end or you like to see it on your device, that's fine. But if you're one who only logs in to answer the multiple choice questions or to give the little thumbs up or the question mark, there aren't any questions today. Just forewarning you. So one of the things that I described to you was that we can change orientation angle, we can change the magnetic field strength, or we can change the area. What we're about to discuss is, William talked about earlier that changing the induced EMF is going to change the buildup of where the charge is. But so far, all we had talked about were loops. Well, what ends up happening is if you move even just a block of conductive material through a magnetic field, you could imagine what's happening here is that the velocity, if you could take a snapshot, say a 1 millisecond snapshot or a 10 millisecond snapshot, then that bar, that rod, has subtended some area in that magnetic field. And so what ends up happening is even if you don't have a coil, a loop of conductive material, you can still get induced EMF just by moving the conductive material through the magnetic field. Motional EMF is going to pay attention to how a current loop moves with respect to a magnetic field. And because we live in a world where relativity exists, even in a classical sense, Galilean relativity, you could imagine that what is happening is that the loop itself is not, or the block itself is not moving, but instead a magnetic field is moving past the wire. So it's going to give some sort of deflection of the magnetic field. That's a bit much at this point, but just something to keep tucked into the back of your head. So in this case, the simplest example that we can think of, motional EMF, is a rod moving through a uniform magnetic field, in which case the flux that is subtended by the moving rod is going to be equal to B, the magnetic field strength isn't changing, times L, the length of the rod is not changing here, but it is changing an area by the mere fact that X is changing as a function of time. And so the rod gets an induced EMF by sweeping out this area that is equal to B, the magnetic field strength, times L, times the velocity that it travels through the magnetic field. Which means that you can get a very small EMF if it moves very slowly through the uniform magnetic field, or you can get a very large induced EMF if it moves very quickly through the field. Right? If you've ever seen these videos on YouTube, or they're worth, I should put one here. One of the classic examples is where you have something like a guillotine fall, but then you've got a magnet at the very bottom, and it will arrest the motion because you're going to end up getting an induced EMF, and there are going to be eddy currents, and there are going to be all of these other things, but the idea is just by the mere fact that it's moving with respect to the magnetic field, you get an induced EMF, therefore you're going to get some induced magnetic field, and that magnetic field is going to be attracted to the external magnetic field because the poles are going to be opposite, and so you can arrest the motion of quick-moving metal if there is an external magnetic field. Veritasium, he's got a great video at the world's strongest magnet, right? And he puts a sheet of metal on top of the hole to the world's largest magnet, and they turn the magnet on, and he tries to lift that thing up. But he finds it's very difficult to do so. It goes back to this type of phenomenon right here. It's more complicated than that because it's a sheet of metal, not just a thin rod of metal, but the eddy currents produced end up coupling with the magnetic field, and it makes it very difficult to change where that metal is in space. Seeing at least one of you nodding your head, so at least one of you have seen that video. It's worth going and watching. The previous example result can be extended to a rod that completes a circuit such that you've got something like this here. If you move the rod to the right with some speed v, then there would be an induced EMF along the rod here, but that is going to be able to give us, it will in fact act, if you will, as if the rod is a battery, a power supply, and so you end up getting an induced EMF around the coil, and you can get a current that flows around the wire. So you end up getting that as you pull this thing to the right, that there is going to be a current that flows through the loop. A classic problem is, though, what is the resistive force against you pulling on this sliding bar to the right? Because here's the rub. If we get the field induces a current around the coil, that means there is a current flowing, let's say in this case, I think it would be flowing from top to bottom here through the moving rod. But if there's current in a conductor inside of a magnetic field, one of the things we talked about last time is that currents in magnetic field experience forces, just like charges want to be deflected by magnetic fields. And so you end up getting that there is a resistive force here back to the left by the coupling of the current that is induced by the magnetic field back to the magnetic field. Again, layer upon layer upon layer of onion here, but makes for very rich problem solving, which creates headaches in the minds of undergraduate students. Bill? It's not the EMF. Remember, EMF, even though EMF is an acronym for electromotive force, EMF is a voltage. The voltage is just the potential for charge to move around that loop. What's causing the opposing force is now, you remember if you go back to previous class notes, one of the things that we said was if you've got this line of current here, I, and you've got a magnetic field B coming out of the screen here, that looks like so, that's B. Then we said that there was a force equal to I times L crossed into B, right? So in this case, if I take I and cross it into B, there is going to end up being a force F to the left here, right? So if you go back to the slide, the sheer fact that there is velocity here is going to induce an EMF, and if I think about what direction the flux is increasing into the board, so it tries to induce a magnetic field that is out of the screen. And if it induces an EMF out of the screen, then I believe the current is going to be flowing in this fashion around this system, right? So it's going to be flowing counterclockwise. I said clockwise before, but it's going to flow counterclockwise here. Well, that means that there's a current traveling up inside of this rod. And a current inside of a magnetic field produces a force back to the left. It tries to resist the change in flux. If you want to think about where the force comes from, it's that nature abhors change, right? That's the principle of Newton's first law. You could almost think of this as there being an amount of inertia in the system. You can't create current from nothing, right? So you're putting in work by pulling on that bar. I guess I should turn the direction that the screen is. You're putting work into the board that is creating current, but there's a cost to that, right? And that cost is that resistive force. And the harder you pull, the more your EMF jumps up, the more your current jumps up, the more difficult it becomes to pull.
So would you say it's because the current flows in the opposite direction, which causes the opposite?
The other way around. There is an oppositely induced magnetic field that produces a current. Yes. That's Lenz's law. Generators are a practical application of motional EMF. So the idea is if you have some sort of magnetic field here, north and south pole, in which the associated magnetic field lines are in figure B, then the orientation angle in is constantly changing as a function of omega here. In which case, you get that generators make use of a continuously varied angle where theta is equal to omega t. And so as a function of time, you get that the flux constantly changes as NBA cosine of omega t. And so you get constantly changing flux, which means that there is a continuously varied EMF, which means that there's a continuously varied positive and negative current. And now we have, finally, alternating current. Woohoo! Finally. Now, one thing to be aware of that I see students make the mistake on homework, and I've seen them make it on the exam before. Let's write this down really quickly. For the generator, what we had was phi is equal to NBA times cosine of theta, or that was cosine of omega t, right? And we get induced EMF is equal to minus d phi dt, or that's minus d dt, just like we did before, of NBA cosine of omega t. But assuming the number of turns, the magnetic field strength, and the area don't change, that's equal to minus NBA times d dt of cosine omega t. And what is the derivative of cosine omega t? Negative sine omega t. That's what most students say. The negatives are going to cancel out. So you get NBA times the sine of omega t. But there's something missing here. What? Yes, don't forget that you have to do the chain rule here. So you have to do the derivative of the argument, and you get an additional term of omega out front of the sign. So don't forget that when you do these derivatives, that if there is something multiplied onto, or if t has some coefficient or some power or whatever else it might be, you end up having to take the derivative inside of the sine or cosine function as well. And you can see that if we still had, or if I should say, if the omega term was missing, NBA, well, that's units of Weber. That's not units of volts. So we have to have something else here, and it's the term of omega, which has units of hertz, so that NBA in Weber times hertz, you can go through if you really want to and verify that it does equal units of volts. Okay? So don't forget that when you work homework. I see that often in office hours and the like. Okay, moving right along. I have it written out for you here, but it's exactly what we just did by hand on the notebook slide. Yes, I did. Thank you for pointing that out. No, I make the slides, and apparently I thought it was a good idea to point that out last time, but I forgot that I thought it was a good idea to point that out last time. So here we've doubly pointed it out. You're extra prepared now. You could just write on your SIEs that I was just a very diligent professor instead of a forgetful professor. It's a fine line between the two, just like there's a fine line for physicists between like crazy and genius. I gotta tell y'all this. I don't know how much time y'all spend around like little kids. It's difficult for me sometimes being a parent because oftentimes in kids' TV shows, the bad guy is a mad scientist, right? And so on one of the Paw Patrol movies, the villain is a mad scientist. I can't remember what her name is. And so first off, my son, when he watched this movie, was wondering why she was so angry, right? Like, and I said, no, it's not mad as in angry, it's mad as in crazy. I know you don't know the difference between that, so we had to work through that. And then he just thought, well, all scientists must be mad or crazy and mean and villainous, and so I don't like scientists. I was like, no, son, that's not how it is. And he was like, but how do you know? And I said, because your dad, me, I am a scientist. And so then he was like wary of me for a little bit because I'm a scientist. So that's hard. And I was trying to explain like all the scientists that he knows because he knows my colleagues. And then he's like wary of them too. And then he says, but wait a second, I thought you were a doctor. And I'm like, well, I am, but I'm not a medical doctor. Like, I can't, if someone yells out on a plane, is there a doctor in the house? I'm not going to be the one raising my hand, right? Because they're not wanting me to diagnose the death throes of a star, right? Usually there's something more like pertinent going on. So just many layers of toddler confusion there. Do what? You don't know. Ha ha! At least as far as my son is concerned, usually most parents have their children's interests in mind. So maybe I'm a mad scientist to the rest of you guys, torturing you in an undergraduate physics class, but all to make the world of my 4-year-old son a better place. I promise, I don't get any sort of weird sadistic like pleasure in making a class difficult for you. I promise you that. Yes, Jacob. How do you know? I'm just trying to make it where you as engineers come up with the next best thing. Maybe out of something that I say here, you're inspired and you come up with a brilliant new mechanism for ion propulsion, and we can actually start expanding humanity out beyond the confines of Seoul. Like, who knows? Yeah, most of you are going to go design weapons if you stay in Huntsville, so there's that. I did that for 5 years before coming here, but maybe I can inspire you to embrace not the destructive side of humanity, but like the adventurous side of humanity. Maybe, just maybe, if I can quote the Grinch. Or let me quote the Lorax, a different Dr. Seuss. Unless someone like you cares a whole awful lot, things aren't going to get better. They're not. There you go. Just leave that with you today. All right, inductance. Woohoo, we finally made it. Inductance. The idea of inductance, especially self-inductance, comes from two main ideas. First, calculating, measuring the magnetic field inside of a loop is difficult, right? You've already experienced that. Why are we doing this? This is flux, and I already had brained up electrical flux, and now we're doing magnetic flux. And now we're not just worried about what the magnetic flux is, now we're worried about how it changes. The second thing is that magnetic fields are generally related to currents. Okay, currents are easy to measure, so if I can take this idea of flux and link it to the current, well, that would be awesome. So now, what we define is a term called inductance, which we use L for some reason. And we say that the flux is equal to the inductance times the current. So if we can figure out what the inductance is for a particular object, then all we have to be concerned about is what is the current and how is it changing. Electrical engineers, if not good at anything else, are really good at telling me what currents and how they're changing are. You're good at a lot of things. I understand that. I'm picking on you a little bit. But you can tell me what currents are and how they're changing, right? And what we want to show is that the inductance of something tends to be a function of geometry, and if it's a function of geometry, that doesn't tend to change inside of a PCB. So if we look at the change in flux, which is just L times I, and the L doesn't change, then all we care about is how the current changes. And the induced EMF is just going to be equal to minus the inductance, which doesn't change, times the change in current. And oh, by the way, as I already saw him grinning, inductance is measured in henries. So look to him. If you want to know what the inductance is, just count how many there are of him in the room, and you've got inductance. Inductance is measured in henries. Henry, are you an electrical engineer? Okay. Then he's not going to be in your lab. You're not going to have a lot of inductance lying around, I guess. Henries are a great unit, like newtons and joules, like, I don't know. All right. For a solenoid, its self-inductance, remember that flux is equal to NBA. Well, the magnetic field created by a solenoid we showed is equal to mu naught times little n, or that's n over L times I. So you can follow all of my work here. And as you can see, the nice thing about it is, for self-inductance, the magnetic field comes from the current, but to figure out what the inductance is, we have to divide by the current. So for self-inductance, no matter what you're looking at, the current always divides out. That means the inductance is independent of what the current is. And so where I took the derivative before and said that L doesn't change, well, here's the proof. L is always constant for a given geometry, so you don't have to take the derivative of that, because I say that if you do the chain rule, the derivative of a constant thing is 0, so that's good. And so for a solenoid, the inductance is equal to mu naught n squared times A, the cross-sectional area of the inductance, times L, the length through the inductor. So it's a function of geometry. Lowercase n is number of turns divided by the length. Lowercase l is the physical length of the solenoid. If you have a solenoid that is wound 1,000,000 times over a meter, then L is the meter length of the solenoid. Little n is the number of turns, total number of turns in the solenoid divided by how long it is. That's the same L as the length, yeah. So depending on which textbook you use, sometimes they'll report inductance in terms of the total number of turns. Sometimes they'll report it in terms of the turns per unit length right here. I can't remember specifically how your book writes it. If you want to know the inductance of something, then if you're in an upper level or a graduate level E&M class, you have to do really complicated, frustrating integrals usually to calculate inductance. If you're anybody else in the world, you go look it up in a table somewhere. Wires have inductance, current loops have inductance, transformers have inductance, but you go and look them up in a table, or you go and find your most convenient engineering handbook that tells you for a given transformer of a given size and a given number of turns, here's how you calculate it, or here's what the value is. Or you just trust that the manufacturer printed value on the side of it is true, just like you do when you grab a resistor out of the drawer. Now, if things can induce magnetic fields inside of themselves based on current, you can also imagine that there are magnetic fields elsewhere in the universe that also come from currents. And so you can get the mutual inductance between two objects. The mutual inductance, say, between two solenoids that are embedded together, or the mutual inductance between one side of a transformer coil and the other side of a transformer coil. No matter what, they are frustrating to calculate. And again, I would encourage you to look them up. But for a solenoid where one solenoid is inside the other, the mutual inductance between them comes out to be equal to mu naught times the number of turns per length in the inner solenoid times the number of turns per length in the outer solenoid times the length of both of those solenoids, assuming that they have the same length even, which isn't always true, but in your nice undergraduate class where things have a very pleasant textbook solution, even if it's frustrating for you to calculate, they have the same length, times pi times the inner solenoid length squared. Woo. So we get a coupling between different units. But again, this makes it nice that now we only have to worry about how the current is changing in whichever one is producing the magnetic field to get what the induced EMF is in the other unit. So if the current is changing inside of N2, you have some sort of power supply attached to N2 here, the outer solenoid, and it ramps up from 0 to 10 amps over the course of 5 seconds. Then what you can do is you can calculate the induced EMF inside of this inner solenoid here with the mutual inductance times the change in current in the outer solenoid, the change in current with respect to time. So induced EMF inside the inner solenoid is equal to mutual inductance times the change in current in the outer solenoid. Questions on that? Well, as we talked about with Bill, if there is some sort of resistance to the change in magnetic flux, what we discussed before is that's an idea of inertia. But when you consider the work energy theorem, that means I have to exert a force on it. That means I have to do work on the system. That means I have to change the energy state of that system. And what generally happens, and you can go through your textbook derivation to see this, but we can measure the amount of energy stored in the presence of a magnetic field. And because magnetic fields come from currents, we say that the stored magnetic energy is equal to 1/2 times Li squared. Just like the stored electrical energy inside of a capacitor was equal to Q squared over 2C, we've got something similar here. That there is energy stored in the fact that you have a current existing somewhere that is creating a magnetic field that doesn't want to change. And if you divide by the area over which that magnetic field exists, you can also see the derivation that the energy density that exists in a magnetic field is equal to B squared over 2 mu naught. So there is energy in magnetic fields, and there is energy density in magnetic fields. It's just a factor of volume between them. Whew. Layer upon layer of onion. Or if you've ever read Dune, a feint within a feint within a feint within a feint. I don't know. That just pops up. If you read Dune, he likes to reuse phrases. As good as the book is, some of the phrases he reuses over and over and over again can be frustrating. That's all that I've got. If you'd like to post questions or ask questions, that's fine. If you'd like to get out of here as quickly as possible, I promise not to be offended. My world domination plan, if I'm following the Paw Patrol regime, I'm going to import some sort of radioactive meteorite and get special superpowers, not unlike Hulk. So Hulk beast mode, I guess, is my world domination plan.